Welcome everyone to this AMOS webinar on energy and weather, co-hosted with the Monash Energy Institute and the World Energy Meteorology Council. We've got three fantastic speakers lined up for you today, and the event's going to be moderated by Dr. Joanna Spears, who will introduce the speakers in just a moment. After the presentations and questions, we'll invite Peter Degorski to provide some final thoughts, and I'd like to thank Peter for all his work in organising this event. My name's Roger Dargaville. I'm the Vice President of AMOS, and I'm also Associate Director of the Monash Energy Institute. I'm speaking to you from my home in Melbourne, which I acknowledge is on the traditional lands of the Wurundjeri people of the Kulin Nation, and I pay my respects to their elders past, present and emerging. As many of you will be aware, the aim of the Australian Meteorological and Oceanographic Society, AMOS, is to support our members and promote their work, and so opening up new and innovative areas of research is one of the ways that we can do this. And so the purpose of this event, as well as providing interesting insights, is to provide potential collaborations between the energy and weather sector, finding new opportunities to solve what are extremely complicated and challenging problems. We're very fortunate tonight to have Dr. Joanna Spears as our moderator. Jo is a senior climate scientist with Snowy Hydro, where she advises on alpine weather and hydrometeorology, seasonal climate variability, climate change and climate risk. Jo gained her PhD at the University of Queensland in Antarctic meteorology and climatology, and has been an active member of the AMOS community for over 10 years. As a scientist working in the energy industry, she has fantastic insight into how weather and energy interact. I'm very delighted to have Jo hosting this event, and I should point out that Jo has taken time out of her maternity leave to do this event, so we're especially thankful for her making the time. And with that, I welcome you, Jo, and thank you very much.
Great, thanks, Roger. Hopefully we don't have any special appearances in the background tonight. But it is a pleasure to help moderate the webinar today. And thanks also to AMOS for organising, as well as the event partners, so Monash University Energy Institute and the World Energy and Meteorology Council. So first of all, I just want everyone to think about when you switched on your lights this morning, turned the heater on, cranked the coffee machine and powered up your computer for yet another Zoom meeting. Did you think about the weather and climate when you flicked the switches? In my role as a climate scientist for Snowy Hydro, I've certainly learned just how important weather and climate science is in the energy sector. Just to provide some examples, so daily temperature patterns influence the energy demand for heating and cooling. Meanwhile, synoptic weather systems dictate how much solar, wind and hydro is available and how much might be needed from other sources. Extreme weather events such as lightning, strong winds, heat waves and bushfires can all have significant impacts on both energy infrastructure and the capacity for generation. So system operators need accurate weather forecasts to respond to these short-term weather conditions. But then as you move into longer timescales, climate drivers, ocean atmosphere patterns and seasonal climate forecasting is important for planning and decision making. And then obviously as you move further into even longer timescales, climate change and climate risk underpin the reliability and resilience of the entire energy system. So clearly there are complex interactions between weather and climate and our energy systems on a range of timescales. And today we're here to, as Roger said, connect the energy and meteorology communities in the first of hopefully a series of weather and energy webinars. Today's webinar will be a fairly broad and open discussion, and this is reflected in our three speakers from diverse areas. So we've got Alberto Tropoli from the World Energy Meteorology Council, Gilbert Brunet from the BOM, and Asif Bangor from AusNet. So just before we kick off, I'd just like to touch on a couple of housekeeping items for this evening's webinar. So each speaker will have approximately 20 minutes to present, and we will be holding questions until the end of the three talks, and we've set aside about half an hour for questions and discussion. So to ask a question, you need to type your questions directly into the Q&A. If you go down to the bottom of your sort of Zoom window, you'll see a Q&A button. That's for questions. and then I'll read them out. However, there will be an opportunity to have a bit of interaction. So if you would like to ask a question live and you want to be unmuted, please type your question into the Q&A, but then click the raise your hand button. And then once we get to your question, we'll unmute you and ask you to read your question out loud. So without further ado, I'll introduce our first speaker, which is Alberto. So Alberto is the co-founder and managing director of the World Energy Meteorology Council. His career spans several leading roles at institutions such as NASA, the ECMWF, the European Centre for Medium Range Weather Forecasts, the University of Reading, CSIRO, and he's the chief editor and author of several books relating to weather and climate risk in the energy industry. So he's got a great talk lined up tonight, very fitting subject on climate services for the energy industry. So I'll hand over to Alberto to share his screen and present.
Thank you very much, Joanna, and thank you very much also, Roger, Peter, for the invite. And it's a great pleasure to speak to the Australian audience. We are here somewhere in the world, connected through the internet. It so happens that I'm actually based in Brisbane, and it's been a pleasure to be back in Australia for the last 6 months or so. So it's a great opportunity for our family to be back here. So I'm going to talk about specifically a couple of projects actually that are happening in Europe. You will see a map of Europe here. So bear with me. There's a lot about Europe. Hopefully this is going to be useful for Australia as well. I'm trying to draw a parallel towards the end, but most of the things can apply to Australia, I'm pretty sure. So it's in the climate services area, the key thing is to start the conversation. So the co-design has been mentioned in many publications and so on as a key element in climate services development. So with one of our projects a few years ago, we ran a number of workshops. This is an image from there, so excuse the image. But the important thing is that here we see a lot of people, putting a lot of thoughts on the table there or on the panel with all these post-its. And the other important thing is that people are standing because it's important to stand to think more in a dynamic way. And so after the discussion, what happened is that we got actually Lyra quite worried. So one of the participants was Lyra, and then she talked to us about this problem that she was having, and that was something that happened in 2015. And in Europe and everywhere in the world, there are these things called heat waves, and this was July 2015. So you see on the bottom here, the image of the pressure system and the temperature with the colors. So there's a pretty high temperature. On the top, you see that in July 2015, Italy was the whole of Italy was over 3 degrees above the average of the last of the 30 years that were considered there. And also consider that the fact that heat waves are not necessarily picked up by monthly averages. So this is quite an exceptional heat wave in this monthly average. It's not so much the heat wave per se. It's the problem for Lyra was that you can see on the right, that caused a very large spike in the price of electricity in Italy. So from around 50 kind of average, it spiked to 70. So it's about 40% increase in a very short space of time. And so that led to some thinking, can we do something about this? So I'll pause there for a minute because we need to let Lyra sleep over that. And we go now to talk about a bit the World Energy Meteorology Council, just a brief introduction about the organization, very, very briefly. So this was established in 2015. It's based in the UK, and the original working actually was done in collaboration with CSIRO, through some of the conferences that we ran while I was at CSIRO in Canberra. So we started this with the vision to contribute to the global activities of science and energy experts, bringing these two communities together to create a more sustainable world where energy systems work in synergy with our weather, climate, and environment. And you need to have some statement, grand statement like this, and what it means in practice. We can demonstrate briefly here. So first, also just want to say that WEMS is it's like a professional association. The main advantage though is that its membership is free of charge, so everybody's welcome to join. And it's if you go to our website, you'll find instructions, or please get in touch with us. Here is a team, just briefly. So it's a diverse team with communications, data engineer, project officer, software developer, and designers, and our directors also with the expertise in both energy and climate and meteorology. Meteorology, by the way, in some circles is meant to refer to both weather and climate. So sometimes we see them separate, sometimes together. There's a bit of confusion about the terminology, but yeah, we are in the area of looking at what the clouds do, the sun does, and the wind does, and so on. So at various time scales. Back to the activities of WEMC. So we do a bunch of things to do with the dissemination of information, maintenance of climate and energy demonstration tools that I will show in a minute. And we also do project coordination, another thing that I will discuss in a minute, and organization of events like our International Conference Energy Meteorology, which is currently on hold, but it wasn't going to happen this year anyway. So we are in difficult circumstances, we fared relatively well. Other things are publications, particularly I'll point to the central one just because it's free, but all the other publications also are very interesting. Actually, the one on the right also is a magazine, is free. And some of the people also from CSIRO and Bureau of Meteorology and other colleagues here in Australia contributed to the book, particularly the Weather Matters for Energy, for which I'm grateful. And here are some of the projects and collaborators, just to list some. And if you go again on our webpage, you find more. That was a little run over the WEMC, and now I just wanted to emphasize the fact that energy and meteorology are inseparable. So they are inseparable because you can see them acting together at different timescales. So starting from the past, where you have a historical climate, which is used, for example, for severe event assessments or several other things, to the short time frames of passing clouds and thunderstorms, which can affect the production of solar power with sudden drops, for example, to hurricanes on the longer time scales, going to days and months, which can disrupt oil rig operations, which may not be a bad thing for some people, but certainly still a disruption. And then El Nino, which can, for example, changes demanding patterns. Finally, the long-term changes, 20, 30, 50 or more years ahead that are projected. And these are starting to be used, for example, for renewable resource assessment or any other impacts on structure, infrastructure, or planning of energy systems. So having said that, we go back now to Lyra, because yeah, we want to find a solution for her. We don't want to keep her awake all night. And so we started to show to her what seasonal forecast can do. So out of the slide here, we are focusing on the right-hand side, where we have El Nino kind of thing, and the projections also a little bit. So this area of climate and particularly climate services. And talking with Lyra, we showed that we took 3 seasonal forecasting systems from Europe, and we looked at how they compare to observations, and we showed that yes, temperature is the one on the first column. It has a lot of red, which means that it's got a lot of skill, although there is some to do with the trend in the temperature as well. But actually other variables that are relevant for energy, wind speed, precipitation, irradiance, relative humidity, all have a little bit of red in Europe. And we're talking about Europe here. So if you know about a bit about the climate, Europe is actually quite difficult to predict. So that's a good news, first piece of good news for Australia. If Europe can do it, Australia can do much better. So that got Lyra thinking, and actually that led to this project. So out of that discussion, we sat down and said, why don't we apply for a European project? And this is what it is. So the added value of seasonal climate forecasting for integrated risk assessment. And I'll tell you a bit about this, how it works. It's a project funded by the European Union under the H2020 program, and it is running, started in February 2018 and due to finish July 2021, but possibly a bit longer than that due to COVID. And so the essential thing here is that we want to use seasonal forecast, but on top of that, we want to find out what is the value add. So compared to what people are doing now, what is climate forecasting bringing to the table, to the actual solutions that the industry are using? So we basically structured the project around a number of case studies, but I'm talking just about the case study which Lyra is involved in. So the first thing to do, where we spent quite a bit of time, and I won't go into the details of all those discussions, but we had to find out basically where the climate information, and particularly seasonal climate forecast, are introduced in the decision-making system of this particular company. So that led us to create this decision tree. This is a simplified version because the real one cannot be shared, but it just for illustration purposes. We came up with all these lines and find out how we can introduce seasonal forecast in the decisions, and also how we can find out what the value is. So we set up a baseline with which is using the climatology. That's what this company is using at the moment, or was using when we started the project. And then we also compare to what would happen if we know reality very well, and then what happens with the seasonal forecast. And out of that, we calculate the value. In order to do that, we asked an economist to find out what is the best methodology to work out the value. Because in fact, there are many methods, as you can see here listed. There are 6 methods listed here, which could be used to evaluate the value. In this particular case, we assessed that the situation was best dealt with econometric models. So that's what we're going to use. I'm not going to talk about econometric models, but just to give you a flavor of the thought process and actually what is happening in the project right now. Then the next step is to say, okay, now let's go back to our seasonal forecasting system and work out what is the actual skill. And because we didn't want to make our life easy, we said, let's take as many models as we can. We don't just want to trust one single model. We want to take as many models as we can. And we want to do it in a quite an orderly fashion. And that led us to create a database of all seasonal forecasts that are sitting into one machine with a lot of data, terabytes of data, and allows us to compare these models with using the same kind of structure. Of course, nowadays, Copernicus Climate Change Service provides many models already, but the time it takes, first of all, to download the data is quite long, so you wouldn't be able to use it for an analysis on the fly. And so you need to have them on locally. And besides, we're not just using the European models, or NCEP also is part of C3S now, the Copernicus, but we also wanted to use other models. So you see listed, for people who know about seasonal forecast, you see a bunch of names here, but without going into the details, we got more than 10 models from around the world. And we're comparing them here with the plot, which is very complex, but the bottom line is that we are putting them together to find out what is the best combination of these models in order to get the best answer for Lyra. So that's basically the bottom line. I won't say, but basically the result of this exercise is that we don't need all the models. Normally 3 or 4, 5 models are sufficient, but this depends a lot on the region, the variable, and the thresholds you use, and so on. So unfortunately, there is no one size fits all for this type of problems. You have to get your teeth into it and find out. But the important thing is that we have a methodology, and that we are using all this multi-model, more than one model, and that more than one model is normally better than the best model that you can have. Even in the case where you know what the best model is, which is not obvious actually. Okay, so what we do next, we take all those models and we plug them. We are back here to the heat wave, and we go back and say, okay, now what if we now plug all this information we have now and play God and see what happens if we go back and we know everything, and what happens to the system. And it turns out that even with the best seasonal forecast model, you can't get to the anomaly that was predicted. So the red bar here in the middle or on the right is what is being observed. So it's a big, very big anomaly. And we try to predict it 1 month in advance with the light blue here, 3 months in advance with the dark blue, and 5 months in advance. So it's quite ambitious to go 5 months or even 3 months back, but it's an exercise. I mean, it's a project. We're trying to do research and find out what is possible. And at the moment, we're still playing around with this, trying to see how we can boost a bit the performance of the models. But the short answer is that even if the signal is captured, like in this case, it was a pretty strong signal for 2015, and the seasonal forecast model was capturing this signal in the right direction, so it was at least a positive anomaly. It wasn't negative, which could happen, and but the signal is not strong enough to get to the red line. So something, you can trust the models to an extent, but then you have to bring in some expert knowledge to know that, for example, the soil was very dry around that time, and all these other considerations that the model will contain, but not necessarily advance in an appropriate way in this seasonal forecast sense. So this is the first lesson. So we can use the seasonal forecast to a good extent, but yeah, then human intervention has to come. We cannot rely entirely on a machine to tell us the answer to this type of questions. Of course, here we are targeting a specific case, and it's a big signal and all the caveats that go with that. And as we know, we cannot test the system onto one case. All these considerations, but you need to start somewhere. You need to try to set up the system in place in order for it to work in all situations. And you want to check first what it does when there's a strong signal. If there's no option, if there's no luck with the strong signal, then it's likely that it's not going to work in other situations where the signal is weaker. But it's also not a general conclusion, the one I just said. Okay, so out of this, another output of the project is actually a climate service. It's called Climate Service Project. Also, it's in the area of climate service because we want to develop climate services that will be used by people, not just pretty pictures. And so that we are working very closely with the industry to provide visual tools like this. This is one option, but we have several other options, and that's also the strength of our project. We are testing different ways to deliver seasonal forecasts to different users in different ways. And this is applied to this case study. So this is a map of all the case studies we have with all the partners involved and industry partners. So from Shell, Thames Water, Tenet in the Netherlands, Enel, Alteria, and even Celsia in Colombia. So most of them are in Europe, but some, as I said, in Colombia. And we have a variety of cases here to do with the heat waves for the climate, but also we have operations, offshore operations, and so on. So a variety of case studies to test how the value of the forecast is, and how we can deliver this eventually in a real way, these climate services. And if you go to the website, you can find a lot more about all these case studies, and they are presented in this kind of uniform fashion with 4 pages each, and they describe, they follow the same structure, so easy to follow. Once you read one, you read all of them, and we'd be happy to get also some feedback. Or if you want to provide some input, you'd be very welcome to do so. Now switching to, and I think, don't know about the time, but yeah, I'll keep going. I'm switching, this is a shorter part. It's about another project or contract, and it's under the Copernicus Climate Change Service, which I mentioned. And this is about an operational service for energy. So this is basically producing data on a regular basis for indicators that are relevant for energy, but obviously starting from climate. And we do that for 3 streams, we call them. One is the past, so we look at what happened in the last 40 years or so. We look at the near future with seasonal forecast, similar to what we just said, and also climate projection. So we have these 3 time scales. Again, this is currently for Europe only, but we are looking to expand also to the rest of the world. We have climate variables indicators here: temperature, wind speed, precipitation, solar radiation, and mean sea level pressure, particularly because are relevant for energy. And we model electricity demand, wind power, both onshore and offshore, photovoltaic production, hydropower production, both run-of-river and reservoir. And the partners at the bottom are those that have contributed to this project, which has just ended formally, but there's a follow-up as well. So it was a 2-year project, ended in April 2020. Some of the products, just to give you a flavor of what has come out of this. So one of the practical applications, let's say, of these products are, for example, looking at the solar radiation. And for Europe, there is this projection that the solar radiation pattern will change in the future. So looking at 81 2010 in the past, compared to 2035, 2064, so 30 appears in the past and 30 years in the future. And we see that basically the solar radiation in the Northern Europe is going to decrease. It's not so obvious, but you can see if you look closely, you see that it's decreasing. And in the south, on the other hand, is projected to increase. So what that means, if we look at, for example, a specific place in southern Europe and in southern Spain, which is, I took that also because it's closer, kind of closer to the latitude of some of Australia. And you see that in terms of solar radiation, there is this, maybe there's a lot of noise. The shading is to do with different projection models. But there is an underlying trend that increases in the future for solar radiation. So you may think this is good news for solar production, because more solar radiation is going to give us more solar power. And you're going to run to your bank and say, look, I now got more solar power, give me more money to build my solar farm. However, what happens in this case is that if you look at also the production overall, that was solar radiation. If you look at production, which accounts also for the temperature effect, then the production is pretty flat. And that's because the temperature, which I'm not showing here, the temperature in Southern Europe is also projected to increase. So the effect of increase of solar radiation is going to be counterbalanced essentially by the increase in temperature, which is going to reduce the efficiency of the panels, and in this projected scenario. Okay, so that's a simple example, but just to bring things closer to home here in Australia, this is an old study we did. But just to say that, you know, like if Europe can do something about seasonal forecast, Australia can do much more, particularly because if you look at the difference between what happens during El Niño, La Niña, for solar radiation, like in this case, you can get differences of larger than 10% on a seasonal basis, which is quite a large difference. So given also that seasonal forecast skill is higher in Australia than in Europe, you put 1 and 1 and you get a good recipe for building a system that allows you to predict, for example, in this case, the solar power for Australia. And one thing that can be used is also this tool that has been developed to really explore various options, various climate variables, energy variables, and combination of them at different time scales, different resolutions. So you can go down to lower resolution here and look at the plots, download. You can also download the data and the plots themselves. Again, this is for Europe, of course, as you can tell, but we are working hard to extend it also to the rest of Europe. So, sorry, the rest of the world. So please keep an eye on that. And just wanted to thank you for your attention, and in particular thanks also from Lyra, who can now rest because we found at least temporarily a solution for her problem of the seasonal forecast and the spike on the electricity price. And I would like to also add that now that I'm in Brisbane, and unfortunately given the situation, I haven't been able to go out much. If you're in the area, you'd like to talk more about how we can use seasonal forecasts or projections, or advance also the tools that you've seen, you'd be very welcome to contact me and perhaps go out for a coffee. And with that, I'll stop. I'll pass it over back to Joanna. Thank you.
Thanks, Alberto. That was great. It was really good to learn more about the WAMC. I've got questions, and there's a few coming through on the Q&A, but we will hold those until the end, as I mentioned. So next we have Asif Bangor. So Asif works in the utility sector as an engineering design manager at AusNet Services. He's got more than 23 years of experience in the power engineering sector, providing technical solutions across the environmental, planning, civil, structural, electrical design sectors, and working across Asia Pacific, including Australia and New Zealand. So Asif is also the convener for an international working group on risk management of overhead power lines and extreme weather events, and he'll be talking a bit about this today. So I'll hand over to Asif for his presentation.
So thanks to Joanna, Roger and Peter for this opportunity to share basically what I've learned in my experience and my past working practice in Australia and around the globe. So we're obviously talking about extreme weather events, a subject very close to my, I would say heart, because we're increasingly, witnessing a number of events in the last couple of years, and with that increase or with that impact, comes along other challenges for utilities and asset owners, specifically asset owners within the utility sector that basically own and operate large assets. And when I say assets, these are power assets, and naturally, assets are being constructed as we speak, and they are in service, as all of us know from, simply taking a drive down and looking at these large ladder structures that one may observe and see. These are steel ladder structures on, all the major interconnections that we witness when we're driving on a freeway or when we're coming closer to the city. All of these assets are being owned, managed, and operated by the utilities. Now, extreme weather events, how do they effectively manage their assets in such events is the subject matter of today. So I just prepared a couple of slides and I'll go through it and take some questions probably at the end when Joanna allows us to do so. So this is just a summary slide which gives you an overview of what I'm going to talk about. Now, legacy designs, when I say designs, this is a very broad term, but for power networks, it's basically designs that are mechanical in nature that effectively lead to a civil and structural design for a structure that carries an electrical circuit. Now, all of these assets have a unique way of design. In the past, around in the 1900s, whenever the lattice tower industry started to develop, there were a number of assumptions that were made. These are lattice structures. They're not necessarily fully closed as a building could be, as a column could be. How does wind actually affect their behavior? And these conductors, which are basically connected to these lattice towers, how do these conductors behave in extreme wind events? So legacy designs from the couple of decades back were always based on a simple phenomenon. You have a wind gust, and that applies to your conductor. Conductor sort of swings in the air, and the wind gust is applied on the face of the structure, and therefore you get what's called a load, a wind load on the structure. So in the past, the analogy was pretty much it's just a gust. It's a simple gust that's applied on the frontal face, on a structure. Now, in the recent, past, we've obviously observed that the extreme weather events have taken a bit of a change in pattern. They're not really simply classified as synoptic. We see a lot more tornadoes come around. We see a lot more convective downdrafts. And I'm using all these terminologies because for the people who've read the BOM reports, the Bureau of Meteorological Reports, especially after these incidents in Australia, would see these terminologies pop up, convective downdraft, microburst, tornado. All of these terminologies are now being used more and more. And as an engineer, being responsible to maintain an asset in the power sector, we need to have an appreciation of how to apply these extreme weather events into physical mechanical loads so that our structures, our assets can actually withstand these events. Now, the third bullet point is around utilities. Naturally, if you're building a house and you walk into an old house that you built, that your grandfather has built in the 1950s, naturally the house construction, the code, the wind design would have been based on old standards. Exactly the same thing, nothing different. All of the lattice towers, all of the transmission lines that we have around the globe are all designed from legacy standards. And these legacy standards were developed without the use of these latest convective downdrafts. But the new standards, which are more prevalent these days, and they're coming around with a number of multiple revisions, and you would have noticed probably Australian wind code AS 1170.2 has recently been sent out for public comment. So there's a number of iterations that you would see from the standards coming around in this near future. The other side of the slide talks about increased risk to safety, economy, and reliability. So the question that I would ask is, as an asset owner, if I know my assets are all old, designed in 1950s or 1940s, and they're still standing, servicing my energy requirements, my market operator is happy, they're getting the reliability, but suddenly a thunderstorm comes through, an extreme weather event comes through, knocks off a few towers or knocks off a transmission line, I just go and fix it. Do I really need to worry? Because I can't go and extract the entire asset base that I've designed and constructed in the last 50 years from my network in a day. It won't happen, right? This is economics 101. No market operator, no energy regulator will give you, it simply doesn't stack up. There's the NPV the net present value has to stack up. Now, all of these existing assets, we know are inherently, lack of a better word, weak. But the fact of the matter is, how can we actually reinforce them? How can we assess them? How can we do that risk analysis and then reinforce perhaps certain segments of critical arteries of the network that provide you with the highest reliability? Keep that in mind, and we'll keep going. So the last bullet point there was do nothing. Is there an option for asset owners in Australia or New Zealand or around the globe to do nothing? So just keep that in mind. And on the last slide, I'll show you why the do nothing option is probably not a good idea. All right, so severe weather events. This is just a bit of a snapshot on the past events in Australia. Just look at the timeline: 2009, 11, 16, 17, 20. As recent as January 2020, we have witnessed enough thunderstorms, cyclones, convective downdrafts, tornadoes, and we've seen enough damage impacted by these events to cause this, I'll call it inertia, to call this momentum to start, to say, let's analyze our behavior. Let's discuss on a global level, on what we can do. Now, Seagrade, you would see a name up there that's called Seagrade. This is a French word, and I'm not French, but I think it's Council for Large Electric Systems. Formed in Paris in 1924, I think, not-for-profit organization that links the entire globe, all the asset owners, utility designers, engineers, asset managers, into one common platform, and everybody does research on power lines, on stations, on energy assets. And from their database, I've actually pulled out just a couple of stats for you. 62 major failures in the last 60 years. 58 were severe weather events. 52 of them were designed in the 1950s. And obviously some lines were reinforced, but most lines, fails, they're still in service. And the high intensity, lines were obviously prevalent at the time. So that picture should show you, as I said, picture, it tells you a lot more. As you can see, a lattice tower on the ground. The next slide just gives you a little bit of a breakdown of how these events actually were recorded by the utility owners. Now, this is not a public, it's not a publicly listed document. You have to be a member of Seagrade to acquire that data, but obviously here we can share it for the wider benefit of the community and for the knowledge of this forum. 4 were cyclonic events, 36 were downdrafts, 4 were tornado events, and then you had certain other aspects there listed as well. So point that I'm trying to get at is all of this is in the last 50 to 60 years. Before that, there was no science behind these, there was no appreciation behind the fact that your assets would be exposed to such loads. And therefore there's a need to revamp our standards, Australian standard for wind, to effectively include all of that information. Now, this is just a comparative analogy of the older design standards. It was based on deterministic criteria, fixed loads and a safety factor. And basically the loadings were, all arbitrary loadings for overhead lines. Now, there were limited guidelines applicable. In Australia, there was mostly no mention of high intensity winds. The major expansion of lines obviously happened after 1980s, and that's why, most of the lines are not designed for high intensity winds. And when I say Australia, 9 out of 10 is the same applicable for around the globe. Now, again, older design standards, as you can see, some photos on the right-hand side showing you the effects of the extreme weather events and how they impact the structures. Conscious of time, I'm just keep going. The newer design standards. Now, in newer design standards, we basically have a more realistic view of how wind events actually occur. And we can easily assess using our probabilistic, techniques on the application of these, wind events and apply them on the structural design. This is an example of the recent code. And when I say recent, this was launched in 2010. This was the first overhead line design standard in Australia and New Zealand. Now, as you can see, it specifically talks about the center region is zone 2, and it says every line that gets designed in this center region has to take convective downdrafts into account. Whereas in people in Melbourne and Adelaide, you would see that it's zone 3, which is synoptic and convective. So that whole, dark green is synoptic and convective. In the prior versions before 2010, there was no such map. There was no such definition. That's the AS 1170.2 current standard that gives us a view of the regions and the breakdown. So as a designer, as a utility owner, if I'm designing a transmission line, and when I say design a transmission line, you would see a lot more new transmission lines getting designed between New South Wales and South Australia in the very near future. 1,000 kilometers of a transmission line is being talked at as we speak, and that will cross multiple regions as well. This is just a quick snapshot of the wind speeds given in AS 1170. As a designer, you would choose the return period of your velocity, 200 years return, and you would pick up 43 meters per second. Wind speed, if you're going with a high reliability line, you go 500 years and you would pick up 45 meters per second. However, for comparison, just look at the corresponding wind speed for cyclonic regions in Australia. It's 72 meters per second for a 200 years return wind speed in region D. So you can see there is some science and there is a lot of data that's gone in the development, but there's no information in AS 1170 that talks about the application of convective wind speeds. That's given in AS 7000, which is the line design standard. Then this slide talks about how do we look at carrying out a risk assessment when we're doing design. So we don't look at a design for an overhead line or a substation just as a local entity in a silo. We look at its impact as on a global level. How does the transmission line fit in with the bigger picture? Because as AMO, Australian Energy Market Operator, they have their role to effectively make sure that in their reliability modeling, the effect of the winds, the effect of the extreme weather events is included. And therefore, we have to put an extra lens on designing transmission lines to undertake that. So we look at basically what is the acceptable, tolerable threshold of risk. If I'm designing a line between New South Wales and South Australia, am I just going to take a lower reliability, or am I going to bump up the reliability, add more strain structures, design it in a way that failure, if it occurs at a certain spot, is accessible, and look at it from a holistic risk assessment view. And then obviously we have to manage those higher risks. There is a very big legal liability here if failures obviously are, identified, or a risk of failure is identified. Now, what happened in South Australia in 2016 attracted $1 billion of a loss of revenue. I'm not sure whether you guys remember, but I read somewhere that there was a huge loss to the entire business community in South Australia that led to that loss. And naturally, recovering that loss would be through insurances and others, but it causes huge inconvenience to both the local community as well as Australia on a wider level. Now, the last one is network owners either accept the risk or accept risk and implement emergency response plans. So that's also one thing that we need to look at from an asset owner perspective. Remember the first slide when I said do nothing option? This is why I want to just show you why a do nothing option is probably not a good idea. Extreme weather events, when they happen, just watch actually what happens to the lattice tower carrying electricity just outside your house, if not your house, outside your shopping center or area where you're living. This is what happens. And bang, it's on the ground. So this was a load test that we did in China back in 2014. I was in the control room, and that's why you see that there's a bit of a blurry image. And I had a cup of coffee in my hand, and I just literally spilled the coffee. The tower went down. Average load on the tower is 200 tons per leg. So you can appreciate the amount of stress on these members, one member gives away, the whole structure goes down in a collapse. Now, you might ask me, why is the design so dependent on one member? It's a ladder structure. It's built because it's economical. Don't think it's one structure. These are hundreds and hundreds of these in a transmission line. And when you're designing hundreds and hundreds of these members and towers, you obviously would want to design it economically so that your financiers can finance the project and your builders can build it safely and economically. Hence, every member within that structure is, designed that it bears, it shares the load. Sharing is caring. That's why every member has to really share and pass on the load to the next member. But what if one member gives away and that member is weak, takes the brunt in the extreme weather event, and it's not designed for an extreme weather event? That's what we engineers have to make sure we design into. We need to reinforce our network so that that what you just seen on the screen does not happen. And I think that would be the slide that I would have. And I'm bang on time, I think. Joanna?
Yeah, great. Thanks, Asif. That video of the tower failure is slightly terrifying. No doubt our most recent summer of bushfires in Australia had quite a big impact on lines and towers as well. Okay, so we might move on. Next we have Gilbert Brunet, who is Chief Scientist at the Bureau. So Gilbert joined the Bureau in 2018 as Chief Scientist, where he promotes science and innovation within the Bureau and advocates the Bureau's science and innovation to the wider community. Gilbert is also the chair of the Science Advisory Panel of the WMO, that's a World Meteorological Organization. And today he's talking about seamless weather and climate forecasts for us. So Gilbert, I think you're okay to go, and Roger's going to flick through the slides.
Yes, thank you. So quite pleased, thank you very much for the invitation. I was tasked to provide a sort of a 101 course on numerical prediction. So I'll do that in my first few slides and then try to convey to you this vision of Earth STEM weather and climate prediction and show you where this is probably going in the future. And hopefully that will convince you that there's a lot of potential in numerical prediction for the energy sector. So do you see me now? I'm on the camera, or that's great. Okay. So what I'll do the history of numerical prediction and essentially also what we call weather forecasting. And by giving this insight in the history of weather forecasting, you'll probably understand all the important ingredients to achieve this. Of course, we need to start with the observation, and since I'm Canadian, I have put an example, a bit like Alberto when he arrived 6 months ago. I arrived here 1 year and 6 months ago, and I had to change my slide, but now my slide has essentially Australian example, but I kept this one from Canada. So the first people to start measuring each 6 hours the weather condition in Canada, it was done in essentially in Montreal at the beginning of the 19th century. Also at the same time in Australia, we started to measure weather parameters, temperature, wind, and all that. In Albert in 1840 with Clark Ross, and Charles Todd in Adelaide start doing those meteorological measurements. But very important, so all around the world in developed country, there was measurement of weather variables. But there was something but that's good, but you cannot do really a forecast with having all those dispersed observations. So the first one who really thought about how to do this was the Admiral Robert Fitzroy, which is well known in Australia, which was the captain of the HMS Beagle that we see on the right-hand side here. Well, it turned out also that it may be less known, he founded the Meteorological Service in UK. So what we call now the Met Office was founded by Fitzroy. And Fitzroy in 1854 done this because he said, well, we have all those observations in UK and Europe. So and now we have the telegraph, and that was the first recipe for weather forecasting, is to use the telegraph to bring all the observation that you have around a continent, a country, at the same place, same location, so you can extrapolate the condition of the weather around that country and use it to make a prediction. Next slide, please. So, and that's the only mathematics I'll show you today. So don't be afraid by this. Then we had the observation, but the weather forecasting was done with extrapolation techniques. And the first one to realize that if we solve the problem of a fluid on a rotating planet, that we could solve, if we could initialize those equation, we could predict the weather. And this was done by Abbey, the American Abbey, and Beknes, the Norwegian. And of course, they wrote two nice papers on this problem, but realized quickly that it was impossible to solve those equations by hand and essentially stopped there. But we knew at this point that there was a physical basis to do weather prediction. The next step was, next slide please, was done by Richardson, a physicist, a UK physicist, who essentially thought that we could maybe solve those equations by making approximation and making calculation. And what he's done, this was in the First World War. He wrote a little book explaining how we could do that. And in this book, you have this picture that you see here on the screen, which is a sphere with gallery of people making calculation. At the time, they used to call them computer. People who done calculation were well known and used for doing all sorts of calculation. But then he said, I will fill this sphere, this building, in a spherical form with computers, people calculating, and I'll make the calculation to do a prediction based on the equation that was discovered 20 years before. He calculated that he needed 64,000 people to do those calculations for a 2-day forecast. 64 was really a no-show. He realized that would not be possible to do something like that, and he stopped doing it. But it's important to realize that computing was a big part of weather prediction, and he was the first one to think about what we call now a massively parallel supercomputer. And of course, no one knew that at the time. No one knew how to build such thing. So we need to go to the next slide to follow the story that in the 50s, when the first computers were invented after the Second World War, they were used to do to decode secret message, but also they were used to do calculation for nuclear reaction. But also, when the first computer was available to do some coding, von Neumann, which was a pioneer of modern computer, asked the meteorologist Charney to do a first numerical weather prediction based on this computer, which was called ENIAC. And they've done a 2-day forecast at that time. And it was successful, promising. And Charney worked on this problem from the 50s to the end of the 70s. And he was quite a visionary. He had vision on weather and climate prediction. He said he always thought that first we need to resolve the problem of numerical weather prediction. And then once we do the weather prediction problem, we will do the climate problem. And what he done first was this GARP project. GARP was for Global Atmospheric Research Program. It was an international project to do to advance the techniques of weather prediction based on supercomputing. In '69, Charney, it's a bit funny to say, he thought that the problem of weather prediction would be solved in 10 years, and then he could do the climate problem. But of course, we all well know that it took more than 10 years to do the weather prediction problem. We're still working on this, but he didn't wait for that. And at the end of the 70s, he wrote another program of research about carbon dioxide in climate. And he knew, he was the one who really said that we need to start doing climate projection based on those same models that we use to do numerical weather prediction. I can say that now in 2020, we are quite close to achieve this vision that we can do climate and weather at the same type of resolution. I'll show you an example later. Now, to be quick, in the 60s, what was new and was the definitive and important component of this, we could have observation. We have satellite-based observation that started, and that can be used to initialize those numerical prediction. So that was quite a step forward. I just want to point out that in Montreal, in the 69, this was a PhD of a student called Audrey Robert, which done a first global prediction before other predictions were regional. So that was the creation of first global model, which is now the ancestor of all existing climate model. And I would like to point out also that this collaboration was done with Bill Bourke, which used to be a chief scientist at the Bureau in Australia. So now we have all the ingredients: telecommunication, we have computers, the theory, and the observation. So we'll all have what we need to do a prediction. Next slide. And just like to show you some interesting progress along the years. You can see a graphic which span from the early 1980s to 2014, where you see the skill improvement of the prediction using global numerical prediction at the European Center. And just focus here on the blue curve at the top of the graphic. Higher it is, more accurate is the prediction. And what you see, the thick blue line show you that the skill in predicting the northern hemisphere, the global geopotential at 500 hectopascal have increased systematically along the year. The little blue curve under the thin blue curve was the skill. Yeah, the top one was the northern hemisphere. The one in the southern hemisphere is the one you have under. It used to be more difficult to predict in the southern hemisphere than the northern hemisphere for many years, until the years 2000, where it started to be quite equivalent to predict the southern and northern hemisphere. That we were as good than that we had in the past. And why? Essentially, I like to make the point, it's because of satellite observation. The southern hemisphere don't have a lot of ground observation, but the fact that the satellites are getting more sophisticated in terms of observation permitted the southern hemisphere to catch up the northern hemisphere. And also you can see from that graphic, if you look at the green curve, this is a 3-day, a 7-day forecast. And if you compare it to the 3-day forecast in red, you can see that it took 20 years to improve by 1 day the lead time of the forecast. And this has always been the way to look at this. Essentially, with better supercomputer, better science, we are able to improve numerical weather prediction by 1 day per decade of research and in technological advancement. It's why we wrote a paper in Nature on this, which was called The Quiet Revolution on Numerical Weather Prediction. It's quite slow in progress, but it has a lot of economical and socioeconomic impact. Next slide. Okay, so I think to be fair, this is the first prediction I'm showing now after those introduction. And I would like to do a quiz with you, so just relax a little bit, a few seconds. We have here a weather prediction from the European Center, which is global at 15 kilometers. And it's compared with satellite observation. And I would like to ask you, which one is the observation and which one is the model? And since everyone is mute, I won't be able to get the answer, but I can, next slide, please. I can show you that the right is the model and the left is Meteosat pictures of those infrared observation. And it's almost the same thing. In fact, I would say that the model is more, seem to be more accurate and more fine in detail. So next slide. So we are now in a position to develop those systems, and it goes from monitoring, research, development, operation, and service. And I like to to show you that on the left-hand side, we have all those observations coming from space and from different ground surface, buoys on the ocean, weather station on the continent. And using all those prediction systems, now we can provide a wide scope of different type of service, which goes from disaster warnings, health, industry. I'll say more about this. Let's say wind energy, the energy industry, climate information, weather, of course, ecosystem, agricultural application, and application for biodiversity also. So that's where we are now. Let me give you a few examples now. Next slide. But before I give you an example, I've shown you a global prediction at 15 kilometers. I would like to show you where we are now with the high resolution. And I will give you an example which is quite impressive here. Isaf was talking about tornadoes a few minutes ago. Well, that simulation will be able to show you a tornado developing in a squall line. And this is unique. It's probably the first time I saw that a few months ago. So what you have here is a squall line, precipitation, which is predicted for 2 days, 1 day, 2 days. And it's done by Charmaine Franklin at Bureau Meteorology. And she had a 1.5 kilometer resolution. And on the right-hand side, you have a 400 meter resolution, which is more realistic. Now, next slide. So what you see here is a simulation, a zoom on this simulation. And what you see here is that at 100 meters resolution, we're starting to see tornado forming in that squall line. And this is quite novel and new. So we'll be able eventually in the future point out a squall line that could have probability to develop a tornado as those resolution. But we're far away from there. But it's interesting science. And just to give you a hint where we're going in the next 10 years. Next slide. This has already been discussed by Alberto, but this is an example for the prediction of the next few days. We use at the Bureau different type of source of information from different centers. The European centers is there, the Japanese also is there, and we use multi-model approach like Alberto explained a few minutes before to do prediction, which are more consensus and more robust than just using one model. So this approach is getting more and more popular at different time scale. Alberto shown some at the single time scale, and we do it now for the next few days. Next slide, please. Something else we do also, we can take those numerical prediction system and do a reanalysis 30 years back in the past over Australia, very different resolution. We have a project at the Bureau called BARA, which is using a resolution of 12 kilometers to provide analysis of all sort of variables like wind, temperature, close to the surface. And we have a few regions which are high resolution at 1.5 kilometers. So when we do analysis for 30 years, there's a lot of people are interested by that in the energy sector. Why? So we have a client who essentially was planning to develop a new site for wind energy, and he asked next. I think next slide. I need to next slide. No, you need to come back. Sorry. Yes. So he want to know what was the production of his new site that you want to develop. That's the blue line you see on the right-hand side graphic, okay? And he said, how this compared to other sites which are already existing, okay? So that's the red curve and the green curve. And what you see in gray here is when you have a lot of high temperature hours, where so people start using more electricity. And he could, so by doing this he can see if how well his new site could complement the others, and because it's based on wind. So we can put at the same place different variables to see how this could impact the energy sector. So that was an example of a product or service we provided someone with you doing reanalysis, which was 30 years long. Next slide. We have seasonal prediction at the Bureau, and I won't say anything on this really because Alberto really mentioned that seasonal prediction is very useful, But the good news is in Australia, there's more scale there is in North America or Europe. So there's a quite good potential there for prediction and using it for the energy sector. But I would say more than that, even in the sub-seasonal time scale, in the prediction of a few weeks to 1-2 months, there's a lot of scale also because of the MGO. So there is a lot of potential in Australia to do that sort of service. Next slide. Another service is about a climate change here. What we have here is a wind farm again, but we know the wind farm at different threshold of temperature can be less productive. And this is an example where you see on the left-hand side the capacity to produce electricity from a wind farm when the temperature is getting higher. And higher it is, less productive it can be. So now in the middle, we see a projection, temperature that we have now from 61 to 2020. And that's the maximum temperature that can come 1 in 10 year max, okay? So where we see now essentially is saying that the 10% probability of excess of temperature 44 Celsius. But the projected one down there shows that with climate change, we could get this 10% probability of exceedance of 46 degrees Celsius. And if you use the response to the wind farm to temperature, you can conclude that you will lose in the future 40% of the capacity of your wind farm. And in fact, in the projected future, you will lose completely anything over 46 Celsius. So that helped industry to make long-term decision for investment. That's another type of service we're providing. Next one, please. The way forward. Next slide, and I'll finish on this. Essentially, we have developed a research development plan for the next 10 years at the Bureau, and it will focus on 4 axes. And next, please. The first one will be to focus on regional and urban forecasts. And a lot of the energy sector is very interested by that. They want to have exactly the temperature inside those cities. It means really high resolution modeling and techniques. And the second one is we need to do better with the observation in the Southern Hemisphere, and the Bureau will work more on this, but also to start using very, we call opportunistic observation in urban areas. We need to develop our skill in doing that. Next, please. We will also develop for region and urban regions, we'll develop fully integrated system, prediction system, which means we'll have atmosphere, ocean, and hydrology model. Each city of Australia is fortunate enough to be close to the coast, but that means they can be vulnerable to coastal flood, urban flood, and also from storms and etc. etc. So this integrated system will try to address all those type of events at the same time. And the last one, no, I'll skip that one, but we want to do service in Antarctica also, but I won't talk about this now. And next one is the seamless weather and climate insight. So we need to, once we have those prediction system in place and a very good high resolution, we want to focus also for application in terms of climate science and in a seamless manner to provide forecasts at the season time scale, but also be able to provide to the customers information at the sub-seasonal time scale, the next few weeks, the next few days, in the next hours. The energy sector wants this information of a prediction at all time scale, and we'll provide that in a consistent way, current way. And last slide is really last slide. No, just before. If you want to know more about all this science, there is a book freely available at WMO, which have been edited with 2 other people. It's called Seamless Prediction with Earth System for Minutes to Months. You can access it freely in French, English, or Spanish. And I would recommend to read also the paper in Nature, The Quiet Revolution on the Meteorology Prediction, if you want to learn more about all this. Thank you very much.
Thanks, Gilbert. That was great. I'd just like to thank all our speakers. First up, if we were live, I think we'd all have a bit of a round of applause, but it's not quite possible in this format. But I thought I'd just kick things off with a fairly broad question. Now, if you, Gilbert, Asif and Alberto, just like to unmute for the Q&A.
Certainly.
So all three of you seem to have a fairly global perspective on your, the energy weather nexus. What advantages do you see Australia has or challenges in facing the future energy transition compared to sort of the other areas that you've worked?
Who can start? I can start if you want. Well, certainly coming from North America and being here now, the weather is absolutely another planet. It's very different, of course. You span tropical, you have tropical weather, you have a mandate also in Antarctic, so you have polar, you need to have some polar capacity. So you get probably everything. I would say also, except for polar region like in the Arctic for a Canadian, where we can see the climate change impacting very strongly, I think after that, Australia is in all sort of aspects in terms of drought, in terms of bushfires, even flood event, storms. The climate change is quite present there here. So there is a big challenge. And like I said, there's a lot of opportunities to improve the prediction system in Australia based on a lot of things have been developed in Europe or North America. But certainly here we are really in quite good position at the Bureau, but we still need to do better. And that's what we want to do for the next 5-10 years.
And that's good. And perhaps I may add, Gilbert, on that, just to answer Joanna's question from a network perspective. Australia's current network was built a couple of years back, but it hasn't seen that tremendous growth. There has been growth, but it's been sort of in the last I would say 2 decades. We haven't seen a number of new projects come up. So we are faced with two challenges. One is we've got an aging network that was built at a certain time for a very different population, growth. There was no, the mining boom effectively, and the whole globalization and the growth of Australia, it is evident now that our energy demand is going up. It's not going down. So we've got inherently, older network, and we need to develop a new network. So there are 2 challenges. One is how can we, spend the money from an Australian entity to reinforce the network, at the same time build newer projects. So building newer projects, you would encapsulate the whole climate change, the whole loadings, the projections as Gilbert and Albert talked about. You take that all into consideration. Obviously, economies become a bit harder to satisfy to your operator, but the existing network that needs to be reinforced, that brings another challenge to the economy. And energy operators, AMO, AER, when they see the bill going up, that's where we have to really come together as a community, as an engineering community, as a wider, ANZ knowledge base, to share that projection, that insight, that look, this is enough evidence that we're seeing this happen again and again. We don't want to build it, and gold plate it such that it won't see that load ever. It is real. That's the challenge that I see asset owners face.
So, shall I answer as well?
Yeah, go for it.
Yeah. So I mean, there are many facets to the question. I won't touch on the technological and engineering that Asif just did very well, and also Gilbert in terms of weather and climate. I would just take a different kind of stance. I think Australia is so blessed by God, if there is one, and unfortunately it's blessed in many ways, and Australians decided to look downward before looking upward. So if we follow a scientific line going from downward under the soil, where geology has been king, we should now start to talk with geologists and see whether they would like to make this transition and go upward and look at the sky and the weather and make meteorology more at the front of the next use of energy. the rest is all political. I mean, we can discuss about the cost and all these things. It boils down to willingness to invest, and the resources here, the potential to be world leader. I mean, the boat might have been missed a few times, but I think there's still a time to go on to that and become leaders in some of the technology that are required for the energy transition. Because as you know, as much as we talk about renewables, we are still at small percentages comparatively. So there is still a long way to go. There are still, 20, 30 years at least, and time to develop the technology required for this transition.
Radio, we've got a question from Mark Hardy. Would you like to ask the question yourself, Mark? We can unmute you, I think. Yep, there you go.
Thanks, Joanna. Thank you, Joanna. Yeah, I was interested in looking at the map that I think ASIF put up on the increased frequency of extreme temperatures, and just acknowledging that wind farms tend to perform very unreliably at these extreme temperatures, and solar also less efficiently at these temperatures. I guess this is a question more for us. Do you feel that this puts the climate change could put the viability of the renewable energy industry at risk?
Mark, I think the solar map was put by Gilbert, but I can answer you from a perspective of the extreme weather events that we have currently experienced. The newer design standards that I talked about do provide you with enough information as a designer, as an asset owner, as a builder, to basically undertake forward projection on load and design it in. Now, from a electrical mechanical perspective, it's straightforward. The challenge lies on the legacy designs that I talked about. Perhaps Gilbert, if you can talk about the projection, that'll be good.
Yeah, no, I think it was the wind farm. It was not about solar energy, it's about wind energy, where the windmills are getting less functional when the temperature is high. And of course, I can imagine we can address this with good engineering in the future. So we could probably adapt to that. But saying that, I think solar energy is getting really cheap, and it's probably the direction where we will go more and more in the future. But I think we can adapt such thing. But at this moment, with the existing infrastructure, they need that service, need to manage the grid. They need to have those predictions and help them to manage, knowing if the region will be having a high temperature, then they will need to rely on the region to bring electricity on the grid. So that's my view on this. Of course, the long-term investment should take into account the climate change projection and adapt the structure, infrastructure, and function of that. So it's not just about adaptation, it's about mitigation in real time.
We had some questions emailed in before the seminar. I forgot to forward them to you, but Beth Walton provided a couple of questions. Australian Renewable Energy Agency has announced a 12-month, $2.9 million project for improving weather forecasting for the energy system. I'm paraphrasing a little bit. Would this real-time forecasting be sufficient to stabilise grid loads and curtail the need, as has been suggested, for rooftop solar generation to be prevented from entering the grid at critical times? And if not, what would be required? Does that question make sense to our panelists? Would anyone like to have a go at answering that one?
Yeah, I think I can just answer a part of it, but I think Alberto will be better positioned. I think in terms of technology in terms of the weather prediction, we are very close to be able to provide such information in urban areas, but there's some work to do. But now let's suppose we have the perfect forecast or the perfect information. I'm not too sure how we could deal with that, because the grid is a very complex thing. To model that is very complex. So Alberto, it's you to answer that.
Yeah, thanks, Gilbert. Just to put things into context, yeah, this funding is coming now, but funding for prediction systems of this sort has started more than 10 years ago. Yeah, it's with the Australian wind energy forecasting system. I think the first funding was made in 2007 or thereabout. And so that system for wind forecasting became operational around 2009 and has been, as far as I know, operational since. So it deals with obviously wind farms, large-scale wind farms. Of course, now the problem is different for solar. In the meantime, there was also this solar energy forecasting system that was funded straight after the wind energy forecasting system. And we started, it's a project I was involved in when I was a CSRO, and we started to look at this problem also of the rooftop, because obviously was a period when the generation started to pick up, and in a space of 2 years went to about 4 gigawatt or so. So that was a big problem for AEMO to look at this. Now, I think investment will have to continue for a while, because this is a quite an insidious problem, mainly because they are so diverse. The panels or rooftop are, you know, different dimensions, different orientation, obstructions are different. So you can only essentially work on a statistical level, but things are improving. I mean, not just in Australia, there are people, companies working on this type of forecasting everywhere. So, and it's been shown that, you know, in places like Germany, Italy, Spain, nobody has remained without the kettle or the light on for a long period of time. So nothing dramatic happens. We can deal with that. And there are many ways to do it. There are sky cameras, there are satellite data. You know, there are many technologies that can be used to deal with this problem.
Everyone, just like to ask, I mean, we're here to connect the two communities, and they're very different communities generally. What do you see as, you know, like important to, you know, facilitate the decision making in the industry through weather and climate? In particular, like, uncertainty is a big issue. Like, often in the energy industry, these decisions are black and white, but our you know, weather and climate forecasts have that degree of uncertainty. So how do we get talking in the same language, and particularly when it comes to uncertainty?
Well, for the Bureau, the approach, we have a business solution group where you have people embedded in the at the Bureau of Meteorology, which are knowledgeable and can speak the same language than the energy community. That's probably the first thing to do, is to have people on board who understand the two sides of the, who can sit between the two and understand the needs of the energy sector and the weather and what we can offer also, and to understand very well the uncertainties of what the weather service can provide. And to manage expectation, that's very important also. And I think we do, at the Bureau, we do that with the agricultural sector and other sector. So that's the approach we have. That's, I would say, in a nutshell, but be the first thing you need to do.
Yeah, so if I can add also, this is something that we are dealing directly with in the project I mentioned, the SECLI Firm, the European project. First thing I would say that it's, in some sense, it's true that it's different the way the decisions are done in a company, industrial, or any kind of management decision, but only because in the end you have to take a decision, and that's the end of the line. And it's like when you buy something, when you do anything, you eventually need to do something. It's like a quantum state, you know, you observe it, it's there, and it's fixed. But there is a lot that happens between then and the final decision, even within a company. So you know, there are so many things that they have to take into account. And obviously, if you go there and say, look, this other piece of information is also uncertain, then they start to pull their hair out and they despair. So what actually happens in our case? What we found useful is that particularly when you go to a big company and they have their ways of operating, and they have their models, and they say, for example, we tell them, why don't you run each ensemble member for so many times? So you use each ensemble member to run your decision-making model and see the answer. And they say, this is too expensive. Okay, so let's step back and see what we can do to avoid using the deterministic kind of mean approach and instead use some sort of a probabilistic. So we decided to take, the first step is to take just terciles, say. So you start to look at the distribution and you split it into discrete pieces, but they're not too many. So you make the problem more manageable, but you go in the direction of using the probabilistic forecast. So it's like a long walk. We have to start somewhere. Instead of saying, the only way to do this is to use all the ensemble members, which will scare everybody off, then it's to say, okay, let's see how we can make the first step and go towards that.
We might wrap up. We're running out of time and we don't want to take up too much more of your evening. So I just want to thank our three speakers, Gilbert, Alberto, and Asif again. And I'll just throw to Peter Jaworski for some final words. So Peter currently works at Reputex. Which is a provider of modelling services for the Australian energy market, and his team focuses on developing seasonal weather forecasts. He's mentioned that he's really encouraged to see the enormous amount of talent in Australia that's supporting this energy transition to a sustainable, weather-driven future. And he enjoys seeking explanations about how the energy industry works and also reading about geophysical fluids, he says. So I'll throw to Peter for final words, and yeah, thanks very much from me.
Thanks, Jo. Well, yeah, I think Alberto said it really well at the start. Sometimes it's just about starting up a conversation, sitting or standing. I prefer standing, but you have to start that conversation. It's a difficult area. A lot of stuff falls through the gaps, and get quite taken by what Alberto said about openness. So there's, the WEMC is doing some really amazing open work, collaborative work, and free membership, free books, free ideas. We're building on each other's ideas. And Gilbert can tell us all about the history of NWP and our weather systems and how they're open. And Asif can tell us about how SIGRA and others share a lot of information. So it's going to take a lot of openness and conversation. That's why AMOS is here, to have these discussions. And please get involved. We do have a national conference in Melbourne, but keep in touch in what we're doing there and have an opportunity to continue these conversations. And thanks everyone for tuning in.